In 1949, the world of physics was still grappling with Albert Einstein's theory of general relativity. It had been decades, but the implications were so profound that new discoveries were still being unearthed from his equations. At the Institute for Advanced Study in Princeton, New Jersey, Einstein had a walking companion. A quiet, brilliant logician from Austria named Kurt Gödel. Gödel was perhaps the only person there who Einstein felt was a true intellectual peer. They would walk and talk for hours. And in 1949, for Einstein's 70th birthday, Gödel presented him with a gift. It wasn't a watch or a book, it was a calculation, a new exact solution to Einstein's own field equations. Gödel had discovered something unsettling. He had conceived of a universe entirely consistent with general relativity that was rotating. And in this rotating universe, space-time was so warped that it created pathways into the past. These were not wormholes or hypothetical machines. They were inherent in the fabric of his model universe. He called them closed time-like curves. A closed time-like curve is a path through space-time that an object or person could take to end up in their own past. You could, in theory, take a sufficiently long journey and shake hands with yourself yesterday. Einstein was deeply troubled by this. His own theory seemed to permit something that defied all logic. But Gödel's work showed that traveling to the past wasn't just science fiction. It was, under certain conditions, a mathematical possibility. This discovery opened a Pandora's box of questions. It gave a formal mathematical language to the paradoxes that philosophers had only dreamed of. If you can visit the past, can you change it? And if you change it, what happens to the present you came from? The logical knots Gödel's solution tied are still being debated by physicists and philosophers today. They form the bedrock of every serious discussion about the nature of time itself. Number 17, you can't exist if you prevent your own birth. The first description of the grandfather paradox appeared in a 1943 French science fiction book, Les Voyageurs Imprudents by René Barjavel. Physicist Stephen Hawking proposed a chronology protection conjecture, suggesting a yet unknown law of physics prevents such paradoxes from occurring. In some quantum interpretations, the probability of an event that creates a paradox is exactly zero, making it physically impossible. This is the one everyone knows. It's the starting point for almost all time travel debates. The logic is simple and brutal. You build a time machine, you decide, for whatever reason, to travel back to a time before you were born. You find your own grandfather when he was a young, single man. You then do something to prevent him from ever meeting your grandmother. The result seems straightforward. Your grandfather and grandmother never meet, therefore your mother or father is never conceived. And if they are never conceived, you are certainly never born. But here's the problem. If you were never born, then you could not have grown up, built a time machine, and traveled to the past to stop your grandfather. The act of succeeding in your mission logically erases the possibility of you ever starting the mission in the first place. It's a perfect contradiction. Statement A, you went back in time and stopped your grandfather, and statement B, you were never born, cannot both be true. Yet one seems to be a direct consequence of the other. This isn't a complex physics problem. It's a fundamental breakdown of causality, cause must precede effect. Your birth is the cause of your time travel mission. But the effect of your mission is the cancellation of your birth. The causal chain eats its own tail and vanishes. So how do thinkers get around this? There are a few major schools of thought. The first and perhaps simplest for preserving a single timeline is the Novikov self-consistency principle. Proposed by Russian physicist Igor Dmitrievich Novikov in the 1980s, it states that any events in a region of spacetime with closed time-like curves must be self-consistent. In plain English, the laws of physics will conspire to prevent a paradox. You can travel to the past, but you cannot change it in a way that creates a contradiction. This doesn't mean some magical force of destiny stops you. It means the mundane laws of physics will get in the way. You travel back to stop your grandfather, you pull out a gun, the gun jams, you try again and a bird poops in your eye at the critical moment, making you miss. You try to push him in front of a bus, but you slip on a banana peel and knock him out of the way instead, which is how he ends up in the hospital where he meets your grandmother. The principle suggests that the probability of any action that would create a paradox is 0. You are free to do anything that is part of history, but you are physically incapable of doing anything that would change it. Your free will is an illusion in this context. You can try to change the past, but you will always fail, and your attempts may even be the very thing that causes the past to happen. The second major solution is the many worlds interpretation, first proposed by Hugh Everett III in the 1950s as a solution to quantum mechanics problems. When applied to time travel, it offers a clean escape. When you travel to the past and stop your grandfather, you don't change your own history. Instead, you create a new divergent timeline. In the original timeline, timeline A, everything proceeds as it did. Your grandfather meets your grandmother, you are born, you build a time machine, and you disappear. In timeline B, which you've just created, your grandfather never meets your grandmother, and a version of you will never be born in that universe. You, the time traveler from timeline A, are now an orphan of time, a visitor in a universe that is not your own. The paradox is resolved because your actions didn't erase your origin, they just created a new reality where you have no origin. This is a neat solution, but it comes at the cost of positing an infinite number of parallel universes branching off at every quantum event. A third, less common idea is that the timeline is self-healing. It's like a river. You can throw a rock in it, because a splash, but the river keeps flowing downstream. You go back and stop your grandparents from meeting at a dance. The timeline adjusts. They end up meeting a week later at a grocery store. You try to prevent that, and they end up being introduced by a mutual friend. The universe has a sort of inertia. Major historical events, like your birth, are fixed points, and the timeline will find a way to connect the dots, even if you try to erase the lines. This is more of a philosophical or science fiction concept than a hard physics one, but it offers a middle ground between being completely powerless and shattering reality. Each solution presents its own set of problems, from the nature of free will to the existence of infinite, unseeable worlds. The grandfather paradox remains the entry point because it forces us to choose our poison. It's number 16. An idea can exist without ever being created. The term Bootstrap Paradox comes from a story by Robert Heinlein by his Bootstraps, published in 1941. In philosophy, this is known as an ontological paradox dealing with the nature of being or existence. Some physicists argue that the second law of thermodynamics would prevent a physical object from being trapped in a bootstrap loop indefinitely, as it would degrade with each cycle due to entropy. This is the Bootstrap Paradox. It's different from the grandfather paradox because it doesn't involve contradictions. It involves origins, or rather, a lack of them. It's a causal loop where an object or a piece of information has no discernible beginning. It just exists, endlessly passed around a loop in time. Here's the classic example. A fan of classical music is obsessed with Beethoven's Fifth Symphony. He's also a physicist who invents a time machine. He travels back to the 1790s to meet his hero, Ludwig van Beethoven. He carries a perfect printed score of the Fifth Symphony with him. But when he arrives, he learns a terrible truth. Beethoven is in a slump. He's struggling with his work and has never heard of, let alone written, the Fifth Symphony. Distraught that this masterpiece might never exist, the time traveler takes his printed score and gives it to Beethoven. Beethoven, impressed, copies it out in his own hand, publishes it, and it becomes a world-famous piece of music. Centuries later, the time traveler is born, falls in love with the symphony, builds a time machine, and takes the score back to Beethoven. So, who wrote Beethoven's Fifth Symphony? The time traveler didn't. He just copied it from the score he had. Beethoven didn't. He just copied it from the score the time traveler gave him. The music itself has no point of origin. It was never created. It simply exists in a closed loop. endlessly passed from the future to the past and back to the future again. This applies to information, but it can also apply to physical objects. Imagine a scientist in the future invents a special, durable pocket watch. He gives it to his younger self in the past. The younger self grows up, becomes the scientist, and at the end of his life, he has the same watch to give to his younger self. The watch was never manufactured. It has no factory, no creator. It just is. This is deeply unsettling for physics. Everything in our universe, from a star to a thought, has a cause. The Big Bang caused the universe. A factory caused the watch. A composer caused the music. The Bootstrap Paradox presents a scenario where an effect has no cause. It is its own cause. This isn't a causal loop. From a physics perspective, this is a real problem. The laws of conservation of energy and mass come into question. Where did the mass and energy of the watch come from if it was never built? For information, it's even weirder. Information theory suggests that information cannot be created from nothing. In the Beethoven example, a complex and specific piece of information, the entire symphony materializes without a creative act, or one potential, and rather bleak. Resolution is that this is simply how some things work in a universe with closed time-like curves. The Novikov self-consistency principle would allow for this. The loop is perfectly self-consistent. There is no contradiction. Beethoven receiving the music is consistent with him publishing it, which is consistent with the traveler hearing it and taking it back. It doesn't violate logic, just our intuition about origins. In this view, the universe can contain these uncaused loops, strange as they may seem. Another perspective involves quantum mechanics. At the quantum level, causality can be fuzzy. Particles can seem to appear from nothing for brief moments. Some physicists, like David Deutsch, have suggested that the paradox can be resolved by looking at the probabilities. A self-consistent object or piece of information would have to survive the loop perfectly, which might be a probabilistic impossibility. Any slight change, any degradation, and the loop breaks. A physical watch would suffer wear and tear. A piece of information copied by hand would eventually accumulate errors. Over an infinite number of loops, the object or information would degrade into nothingness, unless it was somehow perfect and immune to entropy, which itself would violate the second law of thermodynamics. The Bootstrap Paradox forces us to question our most basic assumption that everything comes from somewhere. It suggests that time could be a tangled web rather than a straight line, with loops and knots where things can exist without ever having been born. Number 15, you were always part of the past you tried to change. The concept of a fixed timeline is a cornerstone of the block universe theory of time, where past, present, and future all exist simultaneously. The 2004 film Primer, known for its complex portrayal of time travel, heavily features a predestination model where characters struggle against a fixed, unchangeable series of events. The ancient Greek myth of Oedipus is a classic example of a predestination paradox, where his attempts to avoid his fate are the very actions that fulfill it. This is the predestination paradox. It's a cousin to the grandfather paradox, but with a crueler twist. In the grandfather paradox, you try to change the past and create a contradiction. In the predestination paradox, you try to change the past, and your actions are the very thing that causes the past you were trying to prevent. You are not a visitor to the past, you are a feature of it. You were always there. Let's say a tragic fire burned down your childhood home and you were the only survivor. You grow up haunted by this event, you become a scientist, invent a time machine, and your sole goal is to go back to that night and stop the fire. You arrive hours before the fire is set to start. The house is dark and empty, your family is out. You patrol the property looking for the cause of the fire, maybe a faulty wire or an arsonist. As the night grows cold, you light a lantern for warmth and light. While searching the attic, you stumble. The lantern falls, shatters, and the oil spills, igniting the old wooden beams. Horrified, you realize the fire is spreading too quickly to stop. You run out of the house just as your family's car pulls up. You watch in agony as the house is engulfed in flames. You didn't prevent the fire, you caused it. Your trip to the past was not an intervention, it was the mechanism of the tragedy itself. This paradox suggests that the timeline is immutable. It is fixed and unchangeable. There is no free will when it comes to altering history. Any attempt to do so will only result in you fulfilling your role in a pre-written script. It's a closed loop, not of information like the Bootstrap Paradox, but of events. Or the effect, the fire creates a cause, your desire to go back in time, which in turn creates the original effect, the fire. This idea is deeply connected to a philosophical concept called eternalism, or the block universe theory. In this view, time is not a flowing river. It is a solid block. The past, present, and future all exist simultaneously, just like different points in space. Now is just your subjective experience of your slice of the block. When you travel to the past, you are not changing anything. You are just moving your consciousness to a different coordinate in the space-time block. The events at that coordinate are already fixed. They have, in a sense, already happened from the perspective of the block. Your presence in the past was always part of the block. The historical records were incomplete. They didn't mention a future version of you showing up with a lantern because no one knew who you were. But your actions were as much a part of that historical moment as anything else that happened. This paradox eliminates the logical contradiction of the grandfather paradox. There is no paradox if the timeline is consistent. And a timeline where you go back and cause the fire is perfectly consistent. It is, however, deeply troubling for our sense of agency. It implies that we are just actors reading lines, cogs in a machine of causality that we cannot see or understand. Physicists who lean towards the Novikov self-consistency principle would be comfortable with this paradox. It's a perfect example of a self-consistent timeline. The universe doesn't need to jam your gun or, make you slip on a banana peel to prevent a paradox. It simply incorporates your actions into the fabric of history. Your attempt to break the chain of causality only serves to forge one of its links. This is perhaps the most philosophically bleak of the paradoxes, as it robs the time traveler of any power and turns them into a pawn of fate. Number 14, the future is silent because time travel is impossible. The Fermi paradox, originally about aliens, was formulated by physicist Enrico Fermi during a lunch conversation in 1950. A version of this for time travel is sometimes called the grandfather paradox at the macro level, or the chronology protection argument. Physicist Stephen Hawking was a major proponent of this view, once famously holding a party for time travelers on June 28th, 2009, but only sending out the invitations after the party was over. No one showed up. Enrico Fermi, a physicist, once asked a simple question about aliens. If the universe is so vast and old, and life is statistically likely, where is everybody? The silence from the stars is a mystery. We can apply the exact same logic to time travelers. If time travel into the past is ever invented at any point in the future, then where are all the time travelers? Think about it. If in the year 3000 or 10,000 or a million, someone invents a time machine, the past would instantly become a tourist destination. Historians would flock to see the construction of the pyramids. Scientists would want to get a direct sample of dinosaur DNA. And countless others would come back just to see what it was like. Our time should be crawling with visitors from the future. They should be everywhere. We might not recognize their advanced technology, but there would be evidence. There would be unexplainable artifacts, people with knowledge they shouldn't have, and perhaps even overt appearances. Yet, we see nothing. The historical record is completely devoid of credible evidence of future visitors. The silence is deafening. This paradox of the silent future suggests a few stark possibilities. The most straightforward conclusion is that time travel to the past is, and always will be, impossible. It doesn't matter how advanced a civilization becomes, there may be some fundamental law of physics like Hawking's chronology protection conjecture that makes it unachievable. The universe might have a built-in firewall against causality violations. It's not just difficult, it's forbidden. Another possibility is that time travel is invented, but it is so tightly controlled or so dangerous that no one is allowed to use it to visit our era. Perhaps a future government, a temporal police, prevents any interaction with the past to avoid catastrophic changes. Or maybe the cost of energy is so astronomical that a trip is a rare 1 in a billion event, and they choose more significant moments in history to visit. Our time, from their perspective, might just be uninteresting. A third option is that they are here, but they are observing us under a strict non-interference directive, a sort of prime directive for time. They could be so advanced that their observation methods are completely undetectable to us. They could be cloaked, or they could be watching from another dimension. They are here, but we are in a cosmic zoo, unable to see the zookeepers. A more pessimistic view is that humanity simply doesn't survive long enough to invent time travel. Perhaps we destroy ourselves through war, climate change, or some other catastrophe long before we reach that level of technological mastery. The silence from the future is the sound of our own extinction. This is a chilling thought. The absence of time travelers isn't a sign of physical impossibility, but of our own impending doom. Finally, there's the many-worlds solution. Time travel is possible, but every trip creates a new timeline. So when a traveler from the future goes back, they don't arrive in our past. They arrive in the past of a new parallel universe. Our timeline remains pristine and untouched without any visitors because all the tourists are busy creating and populating other timelines. This would mean that time travel is a one-way ticket to a different reality, and a traveler could never return to the exact future they came from. The absence of evidence is not evidence of absence, as the saying goes, but in the case of time travelers, the lack of any credible sign, any displaced artifact, any confirmed sighting across all of human history is a powerful argument. It suggests that, for one reason or another, the past is and will remain a closed book. Number 13a, billiard ball can stop itself from ever being sent. This paradox was conceived by theoretical physicist Joseph Polchinski in 1991 while he was exploring the implications of Novikov's self-consistency principle. It was designed specifically to be a more pure version of the grandfather paradox, removing human agency and free will from the equation. Some solutions in quantum mechanics suggest the billiard ball would arrive from the future with a different spin or velocity, delivering a glancing blow that alters its own path just enough to enter the wormhole, but not enough to create a full paradox. This is Polchinski's paradox. It's a clever thought experiment designed to strip the grandfather paradox of all its human elements like intention, psychology, and choice. It reduces the problem to pure mechanics, a collision of inanimate objects. Here's the setup. Imagine a wormhole, a theoretical tunnel through space-time. One mouth of the wormhole is here, now. The other mouth is in the same location, but 1 minute in the past. Now, imagine you shoot a billiard ball towards the past mouth of the wormhole. Its trajectory is perfectly calculated. It will enter the past mouth, travel through the wormhole, and exit the present mouth. Here's the twist. The ball exits the present mouth on a collision course with its younger self. It's perfectly aimed to strike its younger self just before it enters the past mouth of the wormhole. The collision knocks the younger ball off its path, so the younger ball never enters the wormhole in the first place. But wait, if the younger ball never enters the wormhole, then it could never travel back in time to exit the present mouth and knock itself off course. We have a classic contradiction. The event of the ball entering the wormhole causes the event that prevents the ball from entering the wormhole. It's the grandfather paradox, but with a billiard ball. There's no free will to argue about. There's no gun jamming or slipping on a banana peel. It's just physics, trajectory, and collision. Polchinski designed this paradox to test the limits of the Novikov self-consistency principle. Novikov's principle says that only self-consistent solutions are allowed. So what would a self-consistent solution look like here? For a long time, it seemed like there wasn't one. The paradoxical trajectory seemed to be a valid solution in the laws of motion. However, later analysis by physicists, including Kip Thorne and his students, found that there are indeed self-consistent solutions. They just aren't the ones you'd intuitively expect. For example, a consistent solution might be that the billiard ball comes out of the future and delivers a glancing blow to its past self. The blow is not hard enough to prevent the past self from entering the wormhole, but it's just hard enough to alter its trajectory so that when it eventually travels back in time, it delivers the exact same glancing blow to itself that it just received. The ball still goes through the wormhole and it still hits itself, but the hit is a gentle nudge rather than a direct paradox-creating collision. The ball's history is perfectly consistent. It got hit because it was going to go back in time and hit itself. The numbers work out. It's a consistent causal loop. In fact, it was discovered that for any paradoxical trajectory, there are an infinite number of these self-consistent glancing blow trajectories. This is a profound result. It suggests that the Novikov principle might be robust enough to handle even these stripped-down, purely mechanical paradoxes. The universe doesn't forbid the ball from interacting with its past self. It just forces the interaction to be one that doesn't create a contradiction. The laws of physics themselves would guide the ball onto a consistent path. This also has strange implications for quantum mechanics. In a quantum version of the paradox, the ball might have a certain probability of entering the wormhole on a paradoxical path. The theory suggests that the sum of probabilities of all non-paradoxical outcomes must equal 1, meaning the probability of a paradoxical outcome must be 0. The universe, at a fundamental level, edits out the contradictions. Polchinski's paradox, designed to break the idea of self-consistency, ended up strengthening it by showing how the universe could cleverly find loopholes to preserve its own logical integrity. Your number 12, even small changes, could erase entire worlds. The term butterfly effect was coined by meteorologist Edward Lorenz in the 1960s. He discovered that tiny variations in the initial conditions of his weather models, as small as 0.0001%, could lead to vastly different long-term forecasts. This is a core concept of chaos theory. In a 1952 short story called A Sound of Thunder by Ray Bradbury, a time traveler steps on a butterfly in the Cretaceous period, and upon returning to the present, finds a completely altered dystopian society. This is the butterfly effect. It's not a logical paradox in the same way as the grandfather paradox. It's a paradox of consequences, a problem of scale and unpredictability. The idea is that time is a chaotic system. A tiny, insignificant change in the past could be amplified over millions of years, leading to enormous, unforeseen consequences in the present. The famous example is the butterfly flapping its wings. A single butterfly flapping its wings in the Amazon rainforest could set in motion a chain of events, tiny air currents affecting other air currents, which affect pressure systems, that could ultimately cause a hurricane in Texas a few weeks later. In a system as complex as weather or history, small inputs can have massive outputs. Now, apply this to time travel. You go back to the age of the dinosaurs, you are incredibly careful. You wear a sealed suit, you don't touch anything. But on your way back to the time machine, you accidentally step on a single insect. You kill one prehistoric bug. It seems like the most minor change imaginable, but what are the consequences? That bug might have been the food source for a small mammal. Without that meal, the mammal dies. This mammal was the ancestor of a whole line of species. Without it, that entire branch of the evolutionary tree never exists. Millions of years later, the world you return to is unrecognizable. Maybe humanity never evolved. Maybe intelligent lizards rule the earth, all because of one crushed insect. The problem is one of information and prediction. It is fundamentally impossible to calculate the long-term effects of any change, no matter how small. The sheer number of variables in a system like global history is practically infinite. You couldn't just avoid stepping on bugs. Every breath you take in the past alters the composition of the atmosphere. The heat from your body warms the air around you. The bacteria on your skin could escape and interact with the ancient environment. Your very presence is a contamination. This makes any purposeful change to the past an act of supreme recklessness. Let's say you go back to prevent a terrible war. You succeed. But the war you prevented, for all its horror, had consequences you couldn't see. Maybe two people met in a bomb shelter during that war, and their grandchild grew up to be the scientist who cured cancer. By preventing the war, you've erased that person from existence. The world is at peace, but millions die from a disease that could have been cured. Did you make the world better or worse? It's impossible to know. This paradox suggests two main possibilities for how time works. One is that the timeline is incredibly fragile and chaotic. Any interaction with the past, no matter how small, will shatter the future you know and replace it with something completely new and unpredictable. This is the premise of many science fiction stories. It makes time travel an act of ultimate destruction, as you are essentially destroying your own world every time you visit the past. The other possibility is that the timeline is robust and self-correcting, an idea we've touched on before. In this model, the timeline has a kind of inertia. Small changes are dampened out over time. You step on an insect. Another insect lays a few extra eggs, and the population quickly recovers. The small mammal finds something else to eat. The river of time flows around your small disruption and returns to its original course. Only massive, targeted changes to pivotal historical moments could have a lasting effect. The butterfly effect is a paradox of knowledge. A time traveler has the physical power to change the past, but lacks the cosmic intelligence to understand the consequences of their actions. It turns the time traveler not into a god, but into a fool, a bull in the china shop of history, capable only of breaking things they can never hope to fix or even comprehend. Number 11, destroying a book in the past could violate the laws of physics. This paradox relates to the conservation of information, a principle in physics that suggests information like energy cannot be created or destroyed. The black hole information paradox, championed by Stephen Hawking and later contested by Leonard Susskind and others, is a famous example of this problem, where the apparent destruction of information by a black hole seems to violate quantum mechanics. This is the information loss paradox applied to time travel. It's more subtle than other paradoxes, but just as fundamental. It's based on the principle that information in a physical sense must be conserved. It can't just vanish from the universe without a trace. Let's start with a simple thought experiment. You have a book. This book contains the complete works of Shakespeare. In the future, you have a time machine. You decide to take this book back to the year 1620, a few years after Shakespeare's death, and give it to a scholar. The book is studied, preserved, and becomes part of the historical record. This is a simple bootstrap paradox where the book's information is in a loop. But now let's change it. You take the same book back to the year 1500, long before Shakespeare was born. You find a remote cave and you burn the book, turning it into ash and smoke. You then return to your own time. What happens? The obvious answer is that nothing much changes. The book is gone, but it was just a copy. But here's the problem from a physics perspective. The information contained in that book, the specific sequence of letters and words that make up Hamlet and Macbeth was created in your time. It was the product of centuries of printing, editing, and preservation, all originating from Shakespeare's creative act in the 17th century. When you took that book to the year 1500 and destroyed it, you took information that had a clear causal origin in the 17th century and erased it from existence in the 16th century. The cause Shakespeare writing the plays still exists in the future, but the information in the book has been retroactively destroyed before its cause. The information is gone, but the chain of events that created it is still intact in the future you came from. This violates the idea that information is conserved within a closed system. The universe as a whole is a closed system. You have removed a complex piece of information from the timeline without leaving any trace of its origin. This is different from just burning a book in the present. When you burn a book now, the information is not truly destroyed. It's just converted into a much more chaotic and disordered state in the ash, the smoke, the heat. A super intelligent being could, in theory, reconstruct the book from that data. But when you destroy the book in the past, you prevent its causal chain from ever connecting. Let's make it even simpler. You write a unique random number on a piece of paper. You travel 1 hour into the past and burn the paper. Now, in the present, you never wrote the number down. But 1 hour ago, the information of that number existed and was then destroyed. Well, where did that information come from? It came from an event you writing it down that no longer happened. This is an information orphan. One solution is that this is simply impossible. The Novikov self-consistency principle would prevent it. You would fail to burn the paper. A gust of wind would put out the match, or you would be discovered. The information would be preserved, ensuring a consistent history. Another solution is the many worlds interpretation. When you burn the paper in the past, you create a new timeline, timeline B, in timeline A your origin. You wrote the number, got in the time machine, and vanished. The paper with the number still exists in that timeline's past. In timeline B, a piece of paper mysteriously appears and then burns, and a version of you who never wrote the number continues his day. The information is conserved within each timeline separately. Timeline A has the creation of the information. Timeline B has its mysterious appearance and destruction. No laws are broken within each self-contained universe. The information loss paradox shows that the problems of time travel go deeper than just cause and effect. They touch on the very nature of information and reality. It suggests that history is not just a collection of events, but a block of information that the universe may be fundamentally programmed to preserve, one way or another. Number 10. Knowing your future eliminates your ability to choose it. This paradox is a central theme in philosophical debates about fatalism and determinism. It's the ancient Greek story of Cassandra, who was cursed to foresee the future but never be believed, explores the psychological torment of knowing what is to come without the power to change it. In physics, the block universe model implies a form of determinism where the future is as fixed and real as the past, making choice a purely subjective experience. This is the free will paradox, also known as the paradox of foreknowledge. It questions whether you can truly have free will if the future is already known. This isn't just about time travel to the past. It's about information from the future traveling to the present. Imagine a perfect future viewer machine is invented. It can show you with 100% accuracy what you will do tomorrow. You turn it on and it shows you a video of yourself. Tomorrow at 10 a.m. you will walk to a bakery and buy a croissant. You watch the entire event unfold on the screen. Now, it is tomorrow morning. It's 9:55 a.m. With absolute certainty that in 5 minutes you are supposed to go buy a croissant. The question is, can you choose not to? Let's say you decide to rebel. I will not be a slave to destiny, you declare. I will stay home and eat cereal. You sit on your couch and wait. 10 a.m. comes and goes. You didn't buy the croissant, but if you did that, then the perfect future viewer machine was wrong. Its prediction was false. This means that a perfect future viewer is logically impossible. If you can know the future, you can act against it, thereby invalidating the knowledge. This creates a contradiction. Now let's consider the other option. You say, okay, the machine is never wrong, so I guess I'll go buy that croissant. But is that a choice? You are not acting freely. You are acting based on the knowledge you received. You are compelled to fulfill the prophecy because you believe it to be true. Your action is predetermined by the information from the future. This leads to a logical bind. If you can defy the prediction, the machine isn't perfect. If you can't defy the prediction, you don't have free will. This paradox can be framed as a time travel problem. A time traveler from the future comes to you and tells you that tomorrow you will be in a car accident at a specific intersection at noon. What do? The rational thing would be to stay home all day far away from that intersection. But if you do that, the time traveler's statement becomes a lie. But if they were lying, why would they bother? This is where the idea of a fixed, unchangeable timeline comes back. In a predestination model, the time traveler's warning is the very thing that causes the event. You hear about the accident, so you decide to drive to your friend's house on the other side of town to be safe. On the way, a series of strange detours caused by your deviation from your normal route leads you to that exact intersection at noon, where you get into an accident. Your attempt to avoid your fate sealed it. You had the choice to stay home, but the universe, in a sense, conspired to ensure the known future came to pass. Another solution is the many worlds theory. When the time traveler tells you about the accident, you are at a branching point. If you stay home, you create a new timeline where the accident never happens. The time traveler came from a future in a different timeline, one where you did get into the accident. Both futures are real, but they exist in separate, parallel universes. Your choice is real, and it determines which universal path you follow. The free will paradox cuts to the core of our identity. We experience life as a series of choices. The idea that this experience is an illusion, that our actions are already written in the book of time, is deeply unsettling. It suggests that if time is a landscape that can be viewed from a distance, then we are not the explorers of that landscape, but merely features within it. Number 9. Parallel universes might be the only way to avoid contradictions. The many worlds interpretation MWI was proposed by physicist Hugh Everett III in his 1957 PhD thesis. It was initially met with ridicule, but has since become a leading interpretation of quantum mechanics, particularly in the field of quantum cosmology. According to MWI, there is no wave function collapse. Instead, every quantum measurement causes the universe to split into multiple universes, one for each possible outcome. This isn't a paradox itself, but a proposed solution to many of the others. It's the many worlds escape hatch. The idea is that whenever an action is taken that could create a paradox, the universe doesn't break. It branches. A new parallel universe is created where the new events can play out without contradicting the original timeline. Let's go back to the grandfather paradox. You travel to the past of your own timeline, timeline A. In this timeline, you were born, you built a time machine, and you left. When you arrive in the past and stop your grandfather, you are not altering timeline. Timeline A remains untouched, a universe where you simply vanished one day. Instead, your arrival and actions create a new divergent timeline, timeline B in timeline B. Your grandfather never meets your grandmother. A version of you will never be born in this universe. You, the traveler, are now a permanent resident of timeline B, a man with no history in this new world. The paradox is resolved. You exist because you came from timeline A. Your actions in timeline B prevent you from being born there, but that doesn't affect your own existence. There is no contradiction because the cause your birth and the negated effect, the birth of your counterpart, are in two separate causally disconnected universes. This elegant solution can be applied to almost any paradox, the Bootstrap Paradox. When the time traveler gives Beethoven the music, he creates a new timeline where the music has no origin. In his original timeline, perhaps Beethoven wrote it himself, or it never existed at all. Or the butterfly effect, when you step on the insect, you don't change your own world, you create a new dinosaur-run world, and you are now stuck in it. The free will paradox. When you are told you will buy a croissant, you can choose to stay home. That choice creates a new timeline. The future viewer simply saw one possible future, not the only one. This idea comes directly from quantum mechanics. The many worlds interpretation MWI posits that at every moment where a quantum system has multiple possible outcomes, the universe splits to accommodate all of them. A particle can be in a superposition of being in two places at once. According to MWI, when it's measured, the universe splits. In one universe, it's here. In the other, it's there. Both are equally real. Time travel, in this view, is the ultimate act of creating a quantum divergence. Your arrival in the past is a macro-scale quantum event that forces a split. The appeal of this solution is that it preserves free will and resolves logical contradictions. You can go to the past and you can do whatever you want. Your choices are real and have consequences. The consequence is simply that you create a new universe and can never go home. However, the many worlds escape hatch comes with a massive cost, philosophically and scientifically. It means that there is an infinite or near infinite number of parallel universes. The new universe is created for every single quantum event, every single moment. This is a concept known as exuberant reality. The universe we see is just one single leaf on an infinitely large, ever-branching tree. There is no way to test this. We can't see or interact with these other universes. It is an unfalsifiable hypothesis to many scientists. This is a violation of Occam's razor, the principle that the simplest explanation is usually the best. Positing an infinite number of unseeable universes to solve a time travel paradox seems like a rather complicated solution. Furthermore, it makes time travel a deeply tragic and lonely endeavor. Every trip to the past is a one-way journey into exile. You can never return to the family, the friends, or the world you left behind. You are forever an anomaly, a ghost from a dead timeline. While it might solve the logical problems, it creates a host of existential ones. Number 8. The laws of physics might have a built-in firewall against paradoxes. The Novikov self-consistency principle was developed by Igor Novikov in the mid-1980s, building on earlier work by Russian physicist Yakov Zeldovich. Novikov's work was primarily focused on the physics of wormholes, and the principle was a way to address the paradoxes that such space-time structures would permit. This idea is a form of cosmic censorship, but for causality rather than for black hole singularity. This idea is the Novikov self-consistency principle. It's not so much a paradox as it is a proposed law of nature that simply forbids them. The principle is elegant and powerful. It states that if an event exists that would cause a paradox or any change to the past, then the probability of that event is zero. It's not that it's difficult to do, it's that it is physically impossible. This isn't about fate or destiny in a mystical sense. It's about the cold, hard laws of physics operating in a self-consistent manner. The universe must obey its own rules, and a paradox is a violation of those rules. Therefore, paradoxes cannot happen. Let's apply this to the grandfather paradox. You go back in time to shoot your grandfather. According to the Novikov principle, you will fail. This failure is not a matter of chance, it is a certainty. Your gun might jam. This isn't a random mechanical failure. The specific quantum interactions within the gun's mechanism would be arranged in such a way as to guarantee a jam. If you try to use a knife, you'll trip. If you try to use your bare hands, a sudden heart attack will stop you. The key insight is that in a universe with closed time-like curves, the pathways to the past and future are mutually dependent. What you do in the past affects the future, and what happens in the future affects what you are able to do in the past. There is a feedback loop. The universe will only allow solutions where this feedback loop is stable and consistent. Think of it like a mathematical equation. If you have an equation like x equals 1x, the only self-consistent solution is x equals 0.5. You can't just choose x to be 3 because it wouldn't satisfy the equation. Similarly, the universe only allows for self-consistent histories. A history where you kill your grandfather is like saying x equals 3. It's an invalid solution that the system will not permit. This principle allows for time travel, but it renders the traveler impotent to change anything of consequence. You can be a tourist in the past, you can observe, you can even interact with the past, as long as your interactions are part of the history that already happened. This is where it overlaps with the Predestination Paradox. Your actions in the past are not just consistent with history, they are a part of it. Your attempt to stop the fire is what starts it. Your attempt to stop your grandfather from meeting your grandmother is what introduces them. This resolves Polchinski's billiard ball paradox neatly. The ball can go back in time, but it can only do so on a trajectory that results in a self-consistent outcome, like a glancing blow. Any trajectory that would create a paradox has a probability of 0 and is therefore not a possible path for the ball to take. The main criticism of the Novikov principle is that it feels like a cheat. It simply defines the problem away. It also raises deep questions about free will. If the laws of physics are arranged to prevent me from taking a certain action, am I truly free? Proponents would argue that free will was always constrained by the laws of physics. You are not free to flap your arms and fly because the law of gravity prevents it. Similarly, you are not free to violate causality because the law of self-consistency prevents it. It's just another fundamental rule of the game. The Novikov self-consistency principle paints a picture of a resilient and logical universe. It suggests that time is not a fragile butterfly that can be broken by a careless traveler. Instead, it is a block of steel, unchangeable and eternal. A time traveler can move along its surface but can never scratch it. Number 7. You could get trapped trying to complete an infinite number of tasks. This paradox is a temporal version of Zeno's paradoxes of motion, particularly the dichotomy paradox, formulated by the ancient Greek philosopher Zeno of Elea around 450 BC. The Hilbert's Grand Hotel paradox, a thought experiment about a hotel with infinite rooms, was introduced by mathematician David Hilbert in 1924 to illustrate the counterintuitive properties of infinite sets. This is the Grand Hotel paradox, adapted for time travel. It explores the weirdness that happens when you mix time travel with the concept of infinity. It's less about causality and more about the logical nightmare of completing an infinite series of tasks in a finite amount of time. The original paradox, Hilbert's Grand Hotel, goes like this. You have a hotel with an infinite number of rooms, and all of them are full. A new guest arrives. Can you make room for them? Yes. You ask the guest in room 1 to move to room 2, the guest in room 2 to move to room 3, and so on. Since there is no last room, everyone can move down one, freeing up room 1 for the new guest. Infinity is strange. Now let's apply this to time. Imagine you have a time machine that can make instantaneous jumps. You also have a lamp with a switch. At 11 a.m. you turn the lamp on, then you use your time machine to jump back to 10:59 a.m. At 10:59 you turn the lamp off, then you jump back to 10:58 a.m. and turn it on. You continue this process, jumping back 1 minute at a time, flipping the switch each time. The question is, at 11:01 a.m., is the lamp on or off? You flip the switch an infinite number of times. For every time you turned it on, you later went back and turned it off. For every time you turned it off, you later went back and turned it on. The final state of the lamp is logically indeterminate. Let's make it more personal. It's a paradox of infinite debt. You are broke. At 10 a.m., your future self appears and gives you a $100 bill. You are delighted. At 10:01 a.m., you get in your time machine, travel back to 10 a.m., and give that same $100 bill to your past self. You have just completed a consistent causal loop. The money has no origin, a bootstrap paradox, but the loop is stable. But now let's say at 10:02 a.m., your bookie shows up and demands you pay a $10 debt. You don't have any money because you just gave the $100 bill to your past self. So you come up with a clever scheme. You tell your future self from 10 a.m., when you come back to give me the money, first give me $10, then I'll pay my debt. Then I'll go back in time and give my past self the remaining $90. But your past self needs the full $100 to give to you. This creates an infinite regress. To pay the debt, you need money from the future, but the future needs that money to have come from the past. You are essentially trying to create money from a time loop, and it leads to a logical breakdown. This paradox highlights the problem of supertasks, the completion of an infinite number of steps in a finite amount of time. In normal life, this is impossible. You can't count to infinity. But with a time machine, you could theoretically set up a situation where an infinite series of actions must be resolved. Physicists and philosophers argue that such scenarios are likely impossible. The universe might have a minimum unit of time, the Planck time about 10 raised to the power of 43 seconds, below which the concept of time itself breaks down. You couldn't keep having the time interval forever. At some point you would hit the fundamental limit of space-time itself, and the infinite series would be cut off. Another possibility is that the energy requirements for time travel would make such a scheme impossible. Each jump in time might require a massive amount of energy, and an infinite number of jumps would require infinite energy. The laws of thermodynamics would step in to prevent the logical paradox from ever forming. The Grand Hotel paradox for time travel serves as a reminder that the universe's rulebook has to be consistent, not just with causality, but also with the bizarre mathematics of infinity. It suggests that even if you could travel in time, there would be strict limits on what kinds of recursive self-referential tasks you could perform before the logic of reality itself began to fray. Number 6, meeting yourself in the past could annihilate the universe. The idea of meeting a past version of oneself is a common trope, but the consequences vary wildly in fiction. In some stories, it causes a catastrophic explosion, while in others, it's a non-event. In physics, there's no specific law that forbids two versions of the same matter from coexisting, but the conservation of mass energy principle raises questions about where the extra mass of the time traveler comes from when they arrive in the past. This is the temporal doppelganger paradox. What happens if you meet your past self? The consequences of this encounter are a matter of intense debate and theoretical time travel discussions. The scenarios range from perfectly harmless to universe-endingly catastrophic. The most extreme version is the annihilation theory. This idea borrows from particle physics, where a particle and its antiparticle, like an electron and a positron, will annihilate each other in a burst of energy if they meet. The theory suggests that matter and time-displaced matter might react in a similar way. If you, a collection of particles moving forward in time, were to touch your past self, a collection of the exact same particles at an earlier point in their timeline, the contradiction would be resolved through mutual annihilation. The result would be a massive explosion, converting the mass of both you and your past self into pure energy, according to Einstein's E = mc squared. This is a dramatic and popular idea in science fiction because it provides clear stakes and a built-in danger to time travel. However, there is no real physics to back it up. Matter is matter. The particles in your body are not tagged with a specific time. An electron from the future is identical to an electron from the past. There is no known physical principle that would cause them to annihilate. A more plausible but still problematic issue is the paradox of identity and causality. Let's say you go back and meet your younger self, you decide to give him some advice. You tell him which stocks to buy, which person to avoid dating, and which career path to take. Your younger self follows this advice and lives a completely different and perhaps much better life. But if he lives that different life, he will not grow up to be the same person you are. He won't have the same memories, the same regrets, or the same motivations. Specifically, he might not have the motivation to build a time machine and go back to talk to his younger self. But if he never goes back, then the conversation never happened. This is another variation of the grandfather paradox. Your interaction with your past self erases the conditions that led to the interaction in the first place. To avoid this, you could adhere to a strict no talking rule. You just observe from a distance. But your very presence could be enough to change things. What if your past self sees you? The shock of seeing an older version of himself could change his entire outlook on life. He might become obsessed with the future, or paranoid, or driven to make sure the future he saw comes true. You cannot interact with your own past without altering it. And altering your own past is a causal minefield. The Novikov self-consistency principle would handle this by saying that any meeting with your past self must be one that is already part of your own history. You might remember, as a child, seeing a strange old man who looked vaguely familiar and gave you a cryptic piece of advice. Years later, when you travel back in time, you realize that the old man was you. You are compelled to play your part, to have the exact same conversation you remember, to ensure the timeline remains consistent. The many worlds interpretation also solves this easily. When you meet your past self, you have branched into a new timeline. You can tell him whatever you want, his life will change, and he will grow up to be a different person in this new universe. Your original timeline from which you departed remains unaffected. The temporal doppelganger paradox is ultimately a paradox about the self. Is your identity fixed? Can you change your own nature by intervening in your own history? The physics might be speculative, but the philosophical questions are very real. Meeting yourself forces you to confront whether you are a product of your choices, or if your choices are a product of who you are. Number 5, you could become rich, but at what cost? This paradox, sometimes called the financial time traveler or temporal arbitrage, is a specific application of the broader information paradox. It's heavily explored in fiction as a primary motivation for time travel. In economics, the efficient market hypothesis suggests that all available information is already priced into the market, making it impossible to beat. A time traveler effectively violates this hypothesis by introducing information from outside the system. This is the Bilker's paradox. It's about exploiting future knowledge for personal gain. The most common example is using a time machine to get rich. You get a sports almanac from the future or a list of stock market winners, and you travel back to the past to place your bets. On the surface, it seems straightforward. You become fabulously wealthy. But this seemingly simple act creates a web of complex paradoxes. First, there's the Bootstrap Paradox of the information itself. Where did the information in the sports almanac come from? It was printed in the future based on the results of games that happened in the past. You take that almanac to the past and use it, the information is in a loop, but the problem gets deeper when your actions start to affect the outcomes. Let's say you bet a huge amount of money on a long shot horse to win a race. Your massive bet alters the odds. The bookies get suspicious, the jockey who was maybe planning to throw the race gets nervous and rides his best, causing the horse to win when it might have lost. In this case, your foreknowledge actually helped cause the event to happen. This is a consistent, predestined loop. But what if your actions have the opposite effect? Your huge bet on a small company's stock causes a surge in its price. This attracts the attention of regulators who launch an investigation and uncover some fraud that would have otherwise gone unnoticed. The company collapses and the stock becomes worthless. By acting on the knowledge that the stock would be a winner, you caused it to become a loser. This is a direct contradiction. You have invalidated the information you used. The Novikov principle would suggest that any attempt to get rich that creates a paradox will fail. Your bet will be refused. The stock market will crash for an unrelated reason just before you cash out, or you'll lose the winning lottery ticket. You can only successfully use future knowledge if your use of it is already part of the established, consistent history. Perhaps history records that an anonymous, mysterious figure made a fortune on that horse race. When you go back in time, you are simply stepping into that role. The butterfly effect is also a massive problem. Becoming incredibly wealthy is not a small change. Your vast fortune would have huge ripple effects on the economy and society. You might fund companies that otherwise would have failed or outbid someone for a piece of land where a crucial discovery was supposed to be made. Your very presence as a wealthy person changes the world in unpredictable ways. The future you return to might be drastically different, and not necessarily for the better. The sports almanac you brought with you might now be completely inaccurate for the years after your intervention. There's also a moral and philosophical paradox. If you use future knowledge to get rich, have you truly earned it? You haven't created any value or taken any real risk. You have essentially cheated the system of causality. This can lead to what's called the paradox of diminishing returns. The first-time traveler to do this might succeed, but if time travel becomes common, the system would break down. Multiple time travelers would be betting on the same outcomes, creating economic chaos. Eventually, the market would become so distorted by temporal interference that future knowledge would become useless. The Bilker's paradox shows that even a seemingly simple, selfish use of time travel is fraught with complexity. It suggests that the timeline is an interconnected system, and trying to pull a single thread for your own benefit could unravel the entire tapestry. Number 4, changing the past could erase the person you've become. This concept is related to the ship of Theseus paradox from ancient Greece, which asks whether an object that has had all of its components replaced remains fundamentally the same object. The assimilation paradox applies this to a person's identity, which is composed of memories and experiences. A 2002 film adaptation of H.G. Wells' The Time Machine features a version of this, where the protagonist cannot save his fiancée because her death was the event that spurred him to invent the time machine. This is the assimilation paradox. It's a subtle and disturbing idea about identity. It posits that if you change too much of your own past, you will gradually be assimilated into the new timeline, your memories and personality overwritten until the person who stepped into the time machine no longer exists. Imagine you had a difficult childhood, you decide to use a time machine to go back and fix things. You give your younger self some confidence, you prevent a bully from tormenting you, you help your family avoid a financial crisis. You make a series of small, positive changes. Each time you make a change, you return to the present. The first time you notice small differences. The world is slightly better. You feel happier. But you also notice a flicker in your memory. You have two sets of memories competing, the original, difficult childhood and the new, improved one. You go back again and make another change. You return and the new memories are stronger. The memory of the original timeline is fading, like a dream. You continue this process. You craft the perfect past for yourself. When you return for the final time, you are a different person. You are successful, confident, and happy. You have no memory of the original sad person who was so desperate that he built a time machine. You don't remember the pain, the struggle, or the motivation for your journeys. The paradox is this. The person who now exists is a product of the new timeline. He would have had no reason to build a time machine. The person who started the journey, the original you, has been effectively erased from existence. You have committed a form of temporal suicide, replacing yourself with a happier, more successful version who is a stranger to you. Your success in your mission erases the mission's creator. This is different from the grandfather paradox, which is a stark binary contradiction. The assimilation paradox is a gradual process, a slow erosion of the self. It suggests that your identity is not a fixed thing you carry with you. It is a product of your entire causal history. If you change that history, you change the product. This could manifest in a few ways. One is the memory overwrite model as described. Your brain, existing in the new present, slowly updates itself to be consistent with the new past, just as a computer file is overwritten with new data. Another, more dramatic version is the fading model, famously used in the Back to the Future films. As you change the past in ways that threaten your existence, you literally start to fade away. Your physical form becomes unstable because its causal underpinnings are being removed. You have a limited time to fix the damage before you vanish completely. A solution from the many worlds perspective would be that you are not changing your own memories. When you travel to the past and make a change, you create a new timeline. The person in that timeline who grows up from your younger self will be different. But you, the traveler, are still the same person from the original timeline. You are now just living in a new universe and you retain all your original memories. You will never assimilate because you are not part of this new timeline's causal structure. You are an outsider. The assimilation paradox is a cautionary tale. It suggests that our past, with all its flaws and hardships, is what makes us who we are. To try and erase the bad parts might be to erase the very core of our identity, leaving a hollow shell in our place. It asks whether a life without struggle is worth living if the person living it is no longer you. Number 3, if time travel is possible, who was the first to do it? This is a temporal variation of the chicken and egg problem. It's also related to the concept of technological progression. For any advanced technology, there's a history of development from basic principles to early prototypes to refined models. Time travel, if it's an invented technology, should have a similar history. This paradox questions how that history could begin. This is the first mover paradox. It's a question about the origin of time travel technology itself. It creates a special kind of bootstrap paradox, not about a physical object or a piece of information, but about the very concept and technology of time travel. Let's assume time travel is not discovered by one person in a single breakthrough. Like most technologies, it's developed over decades. Scientists in 2050 develop the basic theory. In 2070, they build a machine that can send a single particle back a few seconds. By 2100, they have a working prototype that can send an object back an hour. Finally, in 2200, they build the first human-operable time machine. But as soon as the machine from 2200 is built, what is the first thing its creators would do? They might go back to 2100 and give the schematics and technical advice to the team building the prototype, saving them decades of work. Now, the prototype is perfected in 2110 instead of 2200. The team from 2110 would then be able to go back to 2050 and help the original theorists with their equations, providing them with the answers they spent years searching for. Now, the theory is perfected in 2055. This new accelerated timeline continues. The team from 2055 goes back and gives the knowledge to an even earlier generation of scientists. This process would continue, with each generation of time travelers accelerating the development of their predecessors. Where does it end? The technology would be pushed further and further back in time. Logically, the schematics for the time machine could be given to Leonardo da Vinci or Archimedes or even an ancient builder. The end result is a time machine that appears to have no inventor. It was not developed. It was given. The knowledge of how to build it is passed down from the future to the past in an endless loop. The technology itself is bootstrapped into existence. There was no first mover, no original inventor who struggled through the process. The invention exists without an act of invention. This paradox questions the nature of technological progress in a world with time travel. It suggests that any technology as powerful as a time machine would inevitably short-circuit its own development timeline. There are a few ways to think about this. One is that this is simply the way it would be. The Novikov principle would allow this, as it is a perfectly self-consistent, if strange, history. The time machine was never invented in the traditional sense. Its existence is a stable time loop. Another possibility is that there is a chronology protections at play. Perhaps the timeline is self-healing and resistant to this kind of technological bootstrapping. Any attempt to give advanced technology to the past might fail, or the technology might be lost or misunderstood. Maybe Leonardo da Vinci would look at the schematics for a fusion reactor and just see them as interesting drawings, unable to comprehend the underlying physics. The technological context of the time would prevent the advanced knowledge from taking root. The many worlds theory offers another way out. When the team from 2200 goes back to help the team in 2100, they create a new timeline. In this new timeline, time travel is invented earlier, but in the original timeline, development proceeded at its normal, slow pace. There is no paradox, just a series of new universes, each with a more accelerated technological history. The first mover paradox reveals how time travel could warp not just personal history, but the entire history of science and ideas. And it suggests that the most transformative invention of all time might be one that, by its very nature, could never have a true inventor. Number 2, you wouldn't be able to talk to anyone in the distant past. The rate of language change is significant. The English of Chaucer's time, 14th century, is largely unintelligible to modern English speakers without special training. Going back further, Old English spoken around 1000 AD is for all practical purposes a foreign language. This linguistic drift is a constant and predictable feature of all living languages. This is The language drift paradox. It's a practical, often overlooked, but critically important barrier to any meaningful interaction with the past. The paradox is simple. Even if you could travel back in time, you would be unable to communicate with anyone. We tend to think of language as static, but language is a living, constantly evolving thing. It changes dramatically over centuries. Think about the English language. If you travel back to London in the 1800s, you could probably get by. The accent and some slang would be different, but the basic structure would be familiar. Now travel back to the time of Shakespeare, around the year 1600, it would be much harder. You might be able to read the written language if you're familiar with his plays, but the spoken pronunciation, the rhythm, and the common vocabulary would be so different that you would struggle to hold a conversation. You would sound like a bizarre foreigner with an incomprehensible accent. Go back further to the time of Chaucer around 1380. You would be completely lost. Middle English is so different from modern English that it requires academic study to understand. Words like han, suit, and eek would mean nothing to you. And if you go back to the year 1000, before the Norman Conquest, you would be listening to Old English. It is a Germanic language, closer to modern German or Dutch than to the English you speak. It is completely mutually unintelligible. The opening of Beowulf, what? We Gardena in Geerdegum would be gibberish. This isn't just about English. The same is true for every language on Earth. The Latin spoken by Julius Caesar is not the same as modern Italian or Spanish. The ancient Greek of Plato is not the modern Greek spoken in Athens today. This creates a paradox of communication. The further back you go to witness major historical events, the less capable you are of understanding or interacting with them. You want to ask a Roman legionary about his life. He won't understand a word you say. You want to warn a village about an impending disaster, your words will be meaningless noise to them. You would be an outsider, a mute. Your advanced knowledge would be trapped in your head. You could learn the ancient language, of course, but that would take years of study, and you'd still likely speak with a strange accent that would mark you as an outsider. This paradox grounds the fantastical idea of time travel in a very mundane reality. It suggests that most of our fictional portrayals of time travelers seamlessly blending in are pure fantasy. A time traveler would be isolated, unable to ask for food, shelter, or information. Their primary experience would not be one of adventure, but of profound alienation. This also has implications for other paradoxes. How can you trigger a butterfly effect with a conversation if no one can understand you? How can you give your younger self advice if you speak a different language from him, assuming a very long time jump? The only solutions are practical ones. A time traveler would need to be a master linguist and historian. Or perhaps a future technology could include a universal translator, though that brings its own set of technological paradoxes. The language drift paradox doesn't break causality, but it breaks the narrative of the time traveler as an active agent in the past. It turns them from a participant into a silent observer, a ghost watching a world they can never truly be a part of. Number one, time travel violates one of the most fundamental laws of nature. The law of conservation of energy, a cornerstone of physics, states that the total energy of an isolated system remains constant. It's a version of the first law of thermodynamics. When a person travels through time, their mass energy is removed from one point in time and added to another, which appears to violate this conservation law on a local level. This is the energy conservation paradox. It is perhaps the most fundamental physical objection to the idea of time travel. It argues that time travel, as typically conceived, violates the law of conservation of mass energy, one of the most sacred and well-tested principles in all of science. The law states that energy cannot be created or destroyed, only changed from one form to another. Einstein showed that mass is a form of energy with his famous equation E equal mc squared, so the total amount of mass energy in a closed system, like the universe, must always remain constant. Now, consider a time traveler. Let's say you weigh 70 kilograms. You step into your time machine in the year 2024 and travel to the year 1888. When you arrive in 1888, the universe of 1888 suddenly has an extra 70 kilograms of mass energy that it didn't have a moment before. You have appeared out of thin air. This is a clear violation of the conservation of energy. And energy has been created from nothing. Simultaneously, back in 2024, 70 kilograms of mass energy have just vanished. You disappeared. This is also a violation. Energy has been destroyed. The problem exists at both ends of the journey. You are creating a surplus of energy in the past and a deficit of energy in the present. Over the entire history of the universe, the total energy might balance out. The energy that disappeared in 2024 appeared in 1888. But at any single moment in time, the law is broken. Physics, as we know it, operates at single moments in time. There are a few proposed ways around this. One idea is that a time machine must operate on a principle of exchange. To send you back to 1888, the machine must simultaneously bring an equivalent amount of mass energy from 1888 to 2024. It might be a volume of air, or dust, or rock. The universe would remain balanced at all times. This would mean that a time traveler doesn't just appear, they displace something else. Another more complex idea involves looking at the universe from a block universe perspective. If the past, present, and future all exist simultaneously, then the time traveler's path is a world line that simply zigzags through the block. From this four-dimensional perspective, no energy is ever created or destroyed. The total energy of the entire block is constant. Your mass is not added to the past. It was always there on that particular path through spacetime. Our perception of a violation only comes from our limited, three-dimensional view of time as something that flows. This solution is elegant, but requires us to accept a deterministic block universe which has its own set of problems for concepts like free will. A third possibility is that the energy for your materialization in the past must be drawn from the immediate environment. You don't just appear, your body is constructed atom by atom using energy and matter from, the air and ground around you. This would be an incredibly complex and energy-intensive process, likely resulting in a massive release of heat and radiation, not the quiet pop of science fiction. Similarly, your departure would involve the deconstruction of your body, releasing its energy back into the local environment. The energy conservation paradox is a sober reminder that moving an object from one time to another is not like moving a character in a story. It is a physical process that must obey the unyielding rules of the cosmos. It suggests that if time travel is possible at all, it must be a far stranger, more violent, and more complex process than just stepping through a glowing door. It is a final fundamental hurdle that separates the dream of time travel from the physical reality we inhabit.